dy dx equals 1 minus y squared in the bracket times tan x. So let's separate the variables then and integrate, see what we get. So the tan dx can come up to be with the tan x, so we get that. And the 1 minus y squared can move from times down to divide on the other side. And that's dy can stay where it is, so there's our integral. Now this thing here is a partial fraction, so let's have a go at that. Here, so let's do a sub-problem then. So we've got 1 over 1 minus y squared. Sometimes I think this does appear in certain tables of standard integrals, but we'll have a go at it from first principles, so to speak. So 1 over 1 minus y squared then. That's the difference between two squares, so it's 1 over 1 minus y times 1 plus y, which we can write as a in partial fractions 1 minus y plus b over 1 plus y. This won't take a moment to do. Multiplied by the denominator then. Let's see what we get. 1 is equal to a, cross multiply, 1 plus y plus b times the 1 minus y when we cross multiply here and here. So put in values. Y equals 1 then will be the first value. 1 equals, this will disappear. 1 minus 1 is 0. 0 times b is 0. So we'll just end up with 2a. So a is a half. There we go. And then we need b. So let's put in the other value. Y equals minus 1 then. See what we get there. 1 is equal to... this one here will disappear now. So we'll be left with 1 minus minus 1, which is 1 plus 1, 2b. So b is a half. So we got a half and a half, so we can go back to our original problem now. So that's good. So what have we got then? So we've got our integral of 1 over 1 minus y squared, which we can write as a half, over 1 minus y, plus b, which is again a half, over 1 plus y, dy, and that's equal to the integral of tan x, isn't it? Dx. There we go. Now let's do the integration then. Nice and easy, everything is. So we get a half. This will be log of the something. But when we differentiate a something, a minus will come out, so I'll need a minus there. Plus a half, log of the something again. And just a 1 comes out there when you differentiate the something, so that's fine. Here, the integral of tan is log of sec of x. There we are. Plus a constant of integration, which I'm going to write as log a because we've got logs all the way through here, so that should make life a bit easier. Times by 2 all the way through, but remembering when I've done that, I'm going to write this term first and second, so we'll get the log of this, take away the log of that, which I can simply write as log of 1 plus y, divide you minus, so it's 1 minus y. So there's divide and you minus, top take bottom, which is what we've got. But I brought the 2 up here. These two are added, so that's a sec x, isn't it? It's 2 log 2 ln a sec x, because we times by 2 all the way through as well. So this is log of, when the 2 comes up to be a power, you can split these component parts into a squared and sec squared x. Now we can, the log of each these values are the same, so the values must be the same. 1 plus y over 1 minus y then is equal to a squared sec squared x. And so now we'll put in our initial conditions. So at x equals 0, y was equal to a half. So let's see what we get then. 1 plus a half is 3 over 2 over 1 minus a half is a half is equal to a squared sec squared of 0. Well, sec squared is 1 over cos squared, so let's put that down. We've got cos squared 0. Cos of 0 is 1, so we're just left with a squared. So this implies then that a squared was equal to, the halves cancel, and it's just 3 over 1, which is 3. Yeah, or a half goes into 3 over 2 3 times. It's the same thing. Square root both sides, and we get a equals plus or minus root 3. There we go. So we can write down our answer then. Finally, final. Here's what we had before. See it? So we got a squared is what we need really. So we don't need that line. So let's get rid of that because we only need a squared here. So that was unnecessary. So we write 1 plus y over 1 minus y is equal to a squared, which is 3, sec squared x. And we could bring the y's up and rearrange for y if we wanted to obtain an explicit solution. But I'm happy with this so far. That's the implicit solution there.